Hello, everybody. Welcome to the Exploratorium. My name's Kathleen, and I'm part of the programming team here. And we're really excited to have all of you here, as well as several folks from NASA's Mars 2020 mission team here to celebrate the first anniversary of Perseverance's landing on Mars. Before we get to Dr. Sunanda Sharma's talk, I do want to acknowledge that the Exploratorium is on unceded territory belonging to the Ramaytush Ohlone people. We recently developed an extensive land acknowledgement with leaders from the Ohlone community, and one takeaway I have from that land acknowledgement is an encouragement to look at the landscape that you're walking through, the things you see around you, the water, the grass, and think about who was on that land before you, the way they took care of it, and how you want to continue in those traditions to make the land and the entire environment available to those in the future in a rich and robust way. But now we're going to go beyond this landscape and talk about one that we're only beginning to learn a little bit about. So today you'll be hearing an overview of what has been going on with Perseverance in this first year. And we have a really fantastic presenter. I'll tell you just a little bit about Dr. Sunanda Sharma. She's an interdisciplinary scientist focused on astrobiology research, and she's currently supporting the Sherlock instrument on the Mars 2020 team. In her research, she aims to understand the limits of life and the detection of biosignatures in extreme and Mars environments. She's passionate about interdisciplinary research and bio-integrated design to promote greater inclusion and understanding across fields and audiences. She's a graduate of MIT for her bachelor's, master's, and her PhD. And I want to also call out, Sunanda will be giving additional talks throughout the weekend, one of which will be digging a lot more into her career path and what she does at NASA. But here we have overview of Percy's first year from Dr. Sunanda Sharma.
Thank you so much, Kathleen. Hey, everybody. I'm so excited to be here and share all of our updates from the first year of Perseverance's time on Mars with you. So welcome everybody who's here and everyone who's online, because I think this is being live streamed. And we have many exciting updates to go through. So today actually marks our 1-year anniversary, so it's today. Everybody please give a round of applause for Perseverance. And so this is a look at all of the different scientific observations we've had so far and the different achievements we've had so far in Jezero Crater on Mars. So first, starting with this little selfie. So this is a look of us when we were at a site where there's a rock called Rochette. And this was on September 10th, 2021. And so you can see there's 2 images that were put together, and you can see the little masthead turning there. And so that was us looking at the rock, which you can see there's 2 small holes at the bottom there. And that was where we abraded and then cored samples. And so those are some samples that we will bring back on our sample return mission sometime in the future. And so this was on the 198th Martian Sol, and I think now we're on Sol 355. So that was a little time ago, and we've made many more improvements since then. So just going through the aims of our mission, we have several different aims and why we are on Mars. So first is to test how aerial, so air flying, and roving on the ground, explorers can work together. Second, explore a diverse landing site in Jezero Crater. Third, seek signs of ancient life, which is what I'm most excited about. Fourth, collect rock samples that we will bring home to Earth sometime in the future. And then fifth, pave the way for human exploration of Mars. So we've had a very, very, very busy first year. So as you may know, our rover has 7 scientific instruments and a whole set of engineering tools that all allow it to operate safely and do science on the surface of Mars. And one of our first steps was to test all of the systems that were there and make sure all the instruments were working as expected, which they were. We've also taken 19 flights to date with our companion, which is the Ingenuity helicopter. And that was a technology demonstration that's the first of its kind. It was the first time that there's been powered flight on another planet. And so that paves the way for some future aerial exploration we can do on Mars and potentially other places as well. So in the middle, you can see a bunch of images that were stitched together to make this video of Ingenuity and its shadow going all the way down. And then we also got down to business actually analyzing and coring rocks that are on the crater floor. So we examined some natural targets. Natural targets meaning we come up to them, we don't do anything to them, and just observe with all of our different instruments what the rock might be and what it looks like to put it into context of all the places in Jezero Crater we're going to. And then we also looked at abraded targets. And so we use all of our different science instruments in different ways. And one, we use an abrasion tool, which can scrape away the surface of rocks. And then we can use some proximity science tools, including the one that I work on that Kathleen mentioned called Sherlock, to look more closely at what the mineral and organics might be inside that rock. So this helps us examine more closely things about composition. And so we use other tools like Pixel and SuperCam to piece together what they're made of, and this informs our understanding of Jezero Crater and Mars in general. And so we've also successfully collected 6 rock core samples, 1 atmospheric sample, and 1 witness tube for sample return. Okay, so first, how did we get here? So this was one of the most thrilling moments, and this is one of the things that inspires me all the time when I see this video, so I hope you feel as moved as I do. So during landing, the rover captured all of this footage of itself with 7 entry, descent, and landing cameras. And this helps us understand how landing and future landings could happen. So this is not only a cool video, but it's really important information for Mars exploration and exploration beyond this planet. And so there's also a message that's coded in the orange and white panels of the parachute, which I'll kind of go back, and then we can look at it again if you can see it. It says, "Dare mighty things." So for the first time, we could see what landing is like on Mars, and this will help us plan for some future missions. So this is our home on Mars, the Jezero Crater. So this is a 28-mile wide crater. It's just north of the Martian equator, and it was selected as the landing site out of 60 different options that the scientists on the team debated for quite a while before we actually launched. We believe it was once flooded with water and home to an ancient river delta. And that's really important because if you can think of river deltas on Earth, so instance the Mississippi River, there's a lot of sediments that are at the bottom of that river delta and a lot of microorganisms, so really tall bacteria, fungi, archaea, things like that, that live in that sediment. And then when they die, they're buried in that sediment. So you could imagine finding another river delta on another planet is exactly where we want to be to find signs of life, such as from those little microbial organisms. So we think that that might have been teeming with life a long time ago, back when it was completely awash with water. And there are also some compositions there that we're particularly interested in, like clays, because those can preserve signs of life very well. So this was our status on Sol 336, and today, as I mentioned, is Sol 355. And so the map shows the locations of the rover and the helicopter at that time. Since then, we sort of caught up, so we're not so far apart anymore. So those are the 2 blue markers that you see on there. And then each of those white dots are where we stopped. So from the Octavia E. Butler landing site at the top, we went south, and then we stopped at a lot of different places to do remote science and proximity science as well. And those white boxes are where we picked up cores. And so you can see we've been making pretty good progress so far on the first part of our mission, the first campaign. And one other fun fact, which I like to put into context because we're not the only rover that's on there, is that our another sister rover, Curiosity, is 2,300 miles away from us from our landing site. So all of us are operating at the same time. So we also set a bunch of different records, which were very exciting for our team. And one of them is related to the fact that Perseverance can drive itself. So as we have moved further into the mission, we use a powerful auto navigation system to make 3D maps of the terrain. So all the ground that's ahead, it's not flat. There's a lot of different rocks and things that are in the way, and we don't want to crash into them. So this auto nav system helps us to navigate all of the different obstacles that we might run into without having people from Earth help plan that. So as we've gotten more time on Mars, we've developed this auto navigation system more, and we've been able to plan routes around these obstacles without needing Earth in the loop quite as much. So this means that everyone on Earth can focus more on the science, on the long-term planning, on different directions that we want to go, and let the rover do its thing by itself. So this is images from one of the rover's navigation cameras, and the images are taken about every 16 feet. And then they were stitched together, so we increased their contrast so you can see the ground versus the sky a little bit more clearly, and stitched them all together to make this movie. So this is what it might look like. If you were sitting on the rover going through Jezero Crater, this is what you might see. So we hit a new speed record of 1,050 feet in a single sol. And that comes to about 0.1 miles per hour in terms of driving. And I know that sounds a little bit slow, but we are the fastest rover that's on Mars. So we're very happy about that. And we've been very productive in terms of data. And as a scientist, I am thrilled about that. That's exactly what I want to see. So the rover has sent back over 50 gigabytes of data, probably much more than that at this point, which is as much as 11 DVDs, though I know that maybe only some people in the audience remember what DVDs are. We have a lot of data now. So the images are one of my favorite things to receive because it helps you imagine a literally different world. So in all of these pictures, you, as a person just looking at them, you can start to understand what Mars looks like now, and maybe even imagine what Mars used to look like billions of years ago when it was covered in water. So you can see the diversity of the pictures that are here. You can see terrain, you can see rocks, and then you can see parts of the rover. And so the images are important not just for us to understand where we are, but to understand the health of the rover itself, and to make sure all the instruments are operating well. So in case a rock gets stuck somewhere, we can take pictures of ourselves and try to figure out how to remove that rock to not cause any problems for the future. And of course, we get a lot of non-image data as well. And so as part of the Sherlock team, we have a camera, which is called Watson, our little buddy that's next to us on the arm. And then we also get spectral data. So spectra are detected information that we get from shooting a laser onto different rocks and then picking up the responses with a little thing called a detector. And then these show up as basically little squiggly lines. And those squiggly lines actually mean a lot. When you first see them, it looks just like noise. But then once you're trained to understand what those mean, every one of those bumps could mean something like quartz or gypsum or a different type of mineral that is in the rock itself. So this spectral and image information together, putting that together is really, really powerful because you get to see what it looks like, but also what might be in it that might not just be visible to our eyes. So correlating this information is a big part of my job and my favorite part of my job too. And so we're not the only group that does that. There are a couple of other instruments that also have spectral data. And once you put together all of the data from 7 different instruments, all of a sudden you have a very good picture of what might be in a rock. And that helps inform our sample collection and then return. And one other thing is that all of these images are all available online. So if you want to see more of Mars, definitely please go to our website. And you can go through the image gallery. We put images up every day, and then people vote for images of the day or images of the week. So we can see what everybody thinks about Mars and what they think is most special and interesting. So one of the other exciting things about Perseverance is that we have multiple technology demonstrations. So one is Ingenuity, the helicopter, as I mentioned. Another is called MOXIE. MOXIE is the Mars Oxygen In Situ Resource Utilization Experiment, which is a mouthful, that's why we always say MOXIE. And this produces oxygen from the Martian atmosphere. And the Martian atmosphere is not like Earth at all. It's much thinner, and it has a lot more CO2. And that means that if a person went onto Mars right now, you would probably not be able to breathe at all. So figuring out how to make oxygen is really important to potentially having humans there in the future, but also to figure out how to do things like burn rocket fuel to return back to Earth, for instance. So MOXIE has been operating successfully, which was a really big, exciting moment for our team. And then this is our major to-do list of things, is to collect these rock samples. So we have 43 tubes, and we want to fill at least half of them for sample return, to bring actual pieces back of Mars rocks to Earth so that we can study them with way more complex tools than we're able to pack onto this little rover. So far, as I said, we've collected 6 different rock samples. And the way that we decide what to pick up is, so we're doing this, we have all these different tools, some that work really close to rocks, some that work further away. And so when we're further away, we kind of scan the environment and see what might be interesting to look at. And then every week, all of the scientists on the team discuss, hey, does this look like an interesting thing? Do people want to go here and understand more what's there? Or should we turn and look at something else? So when we decide, okay, this target looks really interesting, there's some rocks that have interesting formations here, let's go there, we drive towards there, and then we decide on a particular target. So from this whole group of rocks, we pick a single rock, and then from that single rock, we pick a specific target. And on that target, that's where we start to use our abrasion tool. So we scrape away that surface and make like a 2-inch or so diameter spot. And then by scraping off the surface, we've gotten rid of a lot of the sort of material on the outside that would be really affected by the environment. The Martian environment is very intense and it's very harsh, and it can break down things like any signs of life. So we want to go a little bit below the surface so you can start to see anything that might have been preserved in there. And so we've been able to abrade successfully on several different targets and understood a little bit more of the diversity in the area that we've been so far on the crater floor. And then once we abrade, now we have more information with the proximity science tools like Sherlock and Pixel, for instance. And we can say, oh, there are organics in this. And that means, an organic basically means it's a carbon-like compound, and carbon is found in all the life that we know on Earth. So we think that it might be important in terms of what might be a biosignature. So biosignatures are signs of life. All organics are not biosignatures, but we think a lot of biosignatures might be organics. So that's why the whole team gets excited when we start to see organics there. And then once we see those, we decide, okay, this is an important sample, we want to study it more, let's put a rock inside a tube, and then somebody will pick it up, hopefully in a future mission. So these are a bunch of images of the places that we've abraded so far on our path. So all of those red spots are where we've picked things up. There's actually more than is here. This is a slightly older slide. But you can see our first 5 samples on different places. So say Celette, Coulette, Cartier, Robine, Bellegarde, and they've all shown us different things. So every one of the samples, one thing I'm most excited about is they all look really different. And I know that there's diversity in this crater and we don't expect everything to look the same, but considering that we've only driven this far, I'm surprised that we see so many differences between the samples that we've looked at to date. And so this is a process that we're going to keep going on as we move out of the crater floor region and towards the delta. So another fun thing that we're able to do is take selfies. So each of these selfies is not a single picture, it's actually many different images that are stitched together to look like a single selfie. And we can do this with the Watson camera that's on the arm. So these are 2 different ones that we took. The first one is the one that I showed on the first page, so that was from back in September at Rochette. Another one was slightly later. And this, I think the first one had 57 images and the second one is 62. So it's actually quite a lot of image processing that goes together to put these selfies together. But it's the first view of what we look like ourselves on Mars. And so you can see the helicopter in the background of the second one, which is the first time having the family photo all together. So the Ingenuity helicopter made history with the first powered, controlled flight on another planet. It looks really small here, so it's in the corner there. And we have videos that are in the rest of the exhibition, so you can see that actually operating. And we expected the helicopter to only work for 5 flights, and so far it's worked for 19, the most recent of which was on February 7th. So this has far exceeded our expectations, and we're very excited about that. It's flown over 2 miles, 30 minutes of total airtime. It's sent over 2,500 images back, probably even more by this point. And it's working far better than expected, which is really a first, and I can't explain how exciting that is for the future of flight on other planets. And Ingenuity graduated from a technology demonstration to a scout for the operations team. So once we knew that it was working, and it actually hit far past this 5 flights that we were expecting, we can actually build it into the workflow of how we work in the crater on Mars. So Ingenuity can go ahead, and you saw how we're separated for a period of time. Ingenuity scouts ahead to see what the future terrain we might encounter is. And that goes back into our rover planning and our planning of our traverse. So it's now become a really valuable member of our working team. And it can take images from further up than the rover can itself. So this image was from 16 feet above Mars. And you can see it sees like a little corner of Perseverance in the distance. So now the rover is heading for the delta. We've wrapped up the first part of our campaign, and now we're going towards the delta. And a lot of the people on the team are very, very excited to be here because it's one of Jezero's most exciting features. So as I mentioned, the delta is exciting because we think if we will find signs of microbial life, this is where we might find it. Because there's a chance that in this ancient river that was in Jezero, there's sediments that are at the bottom that have now potentially turned into something like rocks. And then we can go to those rocks, abrade them, pick up samples, and also detect things like organics there. So the whole team is very geared up to do planning for the delta, which is happening right now. And so this is the path that we had charted for Perseverance on top of the delta and out of the crater. So this blue line, so you can see the white part is where we've done so far, and now blue is where we're going to go next. And so this will be a new exploration, as all of this is, and we're so excited to see the results that might come from it. And so just to wrap this all together, once again, these are the 5 aims of our mission, and I think that we are moving towards them very, very well. So already we've done a lot on the first one because Ingenuity has been working so well, and we can see how aerial and roving missions can work together. We've been already seeing so much diversity in Jezero Crater so far, just in this green zone campaign. We have found organics so far. There have been a couple of different press releases about this, and Sherlock was one of the instruments that determined that there were organics in some of the samples that we saw back in December. We have already collected 6 samples and a couple of other tubes, and we're well on the way to paving the way for human exploration of Mars. And so you can follow more of our journey and where we are right now with looking at raw images, seeing where Perseverance is right now, exploring with us, and even hearing the sounds of Mars that are all on our website. So I encourage you to do that. Please check that out. And you can also connect with us and build more of a Mars community on Facebook and on Twitter and through the websites. Thank you. So if anyone has any questions, you can shoot them at me, or you can come meet me and Emily and other people.
Is there any evidence or speculation about what happened to all the water on Mars? I mean, I'm just thinking how
Yeah.
things are melting and evaporating.
Yeah. So there's a lot of interesting speculation about that. One of the questions is, could the water actually be in minerals? So one of the things we've seen is hydration that shows up in our spectra that Sherlock sees. You see a signature of hydration, and that means the water was present there. So you'll see something that looks like a sulfate mineral, and then you'll see a bunch of hydration with it. So one of the potential answers might be that the water is actually inside the minerals. But there's also more people who can speak more about that who are actually geologists on that point. Sorry.
If you were to speculate on when sort of the peak of life, if it did exist on Mars, I mean, how long ago was it? Was it millions of years, or, I mean, maybe that's a question you can't answer, but.
That's a hard question.
Okay.
No, I appreciate it though, because I should be thinking about this, and I do think about it all the time, so I appreciate it. I think it's more in the order of billions of years, because that's when we thought it was more watery, but it's really hard to know right now. There's more information that I would need to understand that. Anybody else? You can always feel free to come by and see us at the exhibition later and all through the weekend.
Thank you for this.
Of course. Yeah. Anybody have a favorite part? Do you like seeing all the selfies? Yes? Yeah. Yeah, I am not one of the kids who wanted to be an astronaut, and I'm not one of the kids who was like, I want to work at NASA. I wanted to be a poet and a naturalist, and I loved being outside, and I loved being in nature and just like feeling what that feels like, I guess. And then as I grew up, I realized that there's a lot of art that's in science, especially in images, and that's kind of what brought those two things together for me. So actually, I did my first degree in biology, and I got really in love with microscopes, like building microscopes and looking at life through microscopes, and then learning more about the extremes of life, which naturally moved me towards astrobiology. And so I did the rest of my degrees in an interdisciplinary program at MIT called the Media Lab. And so I was in an architecture group, but I was a biologist. So I built the lab that was there. And then I started learning a ton about synthetic biology and microbiology to figure out how we could make a building microbiome or design a microbiome for a building and then integrate that with Earth better than we currently do. So that I took a little bit of a winding path, and then I got really excited about space, because when you go to microbiology, you can go to astrobiology really easily. And then I did one experiment that went up to the International Space Station, and that just blew up in the whole world of space for me. And so I'm absolutely thrilled to be here now. Thank you so much for the questions.